The second hand on your clock just moved. You felt it happen. You felt the past second end and a new one begin. And somewhere underneath that feeling is an assumption so old and so quiet that you have never once thought to question it. The assumption that there is a now, a single global instant, sweeping across the entire universe at once, turning the unwritten future into the fixed past, moment by moment, everywhere, for everyone, together. That assumption feels less like a belief and more like a fact of existence, as basic as up and down. And it is wrong. Not approximately wrong. Not wrong in some exotic corner of physics you'll never encounter. Wrong in a way that has been proven, mathematically and experimentally, for over a century. Wrong in a way that means the moment you're living in right now is not the same moment as the person's 1,000 miles away. Wrong in a way that means your past may not be gone, and your future may already, in some sense that is difficult to even phrase in English, be there. Tonight, we are going to take that apart slowly, piece by piece, the way it was actually discovered. Not through mysticism, not through guesswork, but through some of the most carefully tested mathematics human beings have ever produced. And by the end, the clock on your wall is going to look like a very small, very local trick your body plays on you, floating inside something much larger and much stranger. Get comfortable. This is going to take a while, and it is going to be worth it. For most of human history, nobody needed a theory of time. You didn't need one. Time was just the thing that happened while everything else happened. The sun rose, the sun set, a person was born, a person aged, a person died, and in between there was a river of duration that carried it all along. The same for everyone, everywhere, without exception. When Isaac Newton sat down in the late 17th century to build the mathematical framework that would describe the motion of everything from cannonballs to planets, he needed a foundation to build it on, and he chose exactly that intuition. He called it absolute time. He wrote that it flowed, in his words, equably, without relation to anything external, meaning that no matter where you stood, no matter what you were doing, no matter how fast you were moving, time ticked forward at the same universal rate. 1 second on Earth was 1 second on the Moon, was 1 second at the far edge of the solar system. There was, in Newton's universe, a cosmic master clock, invisible but real, and every clock everywhere was simply a local reflection of it. This idea worked. It worked so well that it put men on the moon, so well that it is still taught in every introductory physics class on the planet, so well that for over 200 years, nobody seriously doubted it. But there was a problem sitting quietly underneath Newton's equations, and it had to do with light. Light, it turns out, does not behave the way everything else in Newton's universe behaves. If you're standing on a train moving at 60 miles an hour, and you throw a ball forward at 10 miles an hour, someone standing still outside the train sees that ball moving at 70 miles an hour. The train's speed and the ball's speed simply add together. That's common sense. That's how velocities have always worked in a Newtonian universe, but light refuses to play by that rule. In the late 19th century, physicists set out to measure how fast light moved relative to the Earth's motion through space, expecting to find exactly the kind of addition and subtraction that worked for everything else. They found nothing of the sort. No matter which direction they measured it, no matter how fast the Earth itself was moving through the cosmos, the speed of light came back the same, every single time. It didn't matter if you were moving toward the light source or away from it. It didn't matter if you were standing still or racing at thousands of miles an hour. The number never changed. This should not be possible in a universe governed by Newton's rules, and for years, physicists tried to explain it away. Maybe there was some invisible medium interfering with the measurement. Maybe the instruments were flawed. Maybe there was some correction that would make the anomaly disappear. None of it worked. The anomaly was real, and it was telling everyone something they did not want to hear. Velocities do not simply add together the way common sense says they should, and if that's true, then something else in the equation has to be bending to keep the speed of light constant. That something else turned out to be time itself. In 1905, a 26-year-old patent clerk in Switzerland took the anomaly seriously instead of trying to explain it away. And he worked out what had to be true if the speed of light really was the one fixed, unbreakable constant in the universe. If light always measures the same speed no matter how you're moving, then the only way for that to be mathematically consistent is if space and time themselves are not fixed. If they stretch and compress depending on your motion, in exactly the right way to keep light's speed constant for every observer. This is what we now call special relativity, and one of its most direct consequences is something called time dilation. A clock in motion, relative to an observer who is standing still, ticks slower than that observer's own clock. Not because the clock is broken, not because something is interfering with the mechanism. The rate at which time itself passes is different for the two of them. This isn't a philosophical claim. It has been measured directly, repeatedly, with instruments precise enough to catch differences of billionths of a second. In 1971, two physicists loaded 4 atomic clocks onto commercial airliners and flew them around the world, once eastward and once westward, while a 5th clock stayed on the ground. When the planes landed, the traveling clocks and the stationary clock disagreed, by amounts that matched Einstein's equations almost exactly. The clocks that had been moving had genuinely experienced a different amount of time than the clock that stayed still. Every single day since then, this effect has been quietly at work in a piece of technology sitting in your pocket. The satellites that make GPS possible are moving fast enough and sitting in a different enough gravitational environment that their onboard clocks tick at a measurably different rate than clocks on the surface of the Earth. If engineers didn't correct for that difference every single day, the location on your map would drift by miles within hours. Every time your phone tells you where you are, it is quietly relying on the fact that time is not the same everywhere. That fact is not theoretical. It is engineered into the device in your hand. So here's the first thing to sit with before we go further, because it is going to matter enormously in a few minutes. If motion changes the rate at which time passes for you, then the idea of one single, universal now, the Newtonian master clock, ticking the same beat for everyone, everywhere, cannot survive. There is no version of now that is true for the whole universe at once. There is only your now, moving at whatever speed you happen to be moving, inside whatever gravitational field you happen to occupy. Somewhere out there, someone moving differently than you is experiencing a slightly different now, and neither one of you is wrong. Neither one of you is more correct than the other. This is where the story starts to bend away from anything your intuition prepared you for. Now let's push a little further, into something even stranger than time dilation. Something that most people have never been told, even after they've heard the basics of relativity a dozen times. It's called the Relativity of Simultaneity, and it might be the single most disorienting consequence of Einstein's work, because it doesn't just say that clocks run at different rates. It says that two people can genuinely, permanently disagree about which of two events happened first. And both of them can be correct. Picture 2 flashes of lightning striking at 2 different points, far apart from each other. From the perspective of someone standing exactly halfway between the 2 strikes, both flashes reach their eyes at the same instant. And so, for that person, the 2 events are simultaneous. They happened at the same moment. Nothing strange yet. But now imagine a second observer, moving past the midpoint at a significant fraction of the speed of light, heading toward one of the 2 flashes, because that observer is moving toward one light source and away from the other. The light from the flash they're moving toward reaches them slightly before the light from the flash they're moving away from. To this moving observer, the 2 flashes did not happen at the same time. One happened first, the other happened second. And here is the part that breaks Newtonian intuition completely. There is no experiment, no measurement, no piece of information anywhere in the universe that can tell you which observer is right. They are both right. Simultaneity, the very idea of two things happening at the same time, is not a fixed, objective fact about the universe. It depends entirely on how you are moving through it. Now, stretch that idea out across truly enormous distances, because this is where it stops being a curiosity and starts becoming something genuinely disturbing. Physicists have worked out that for two observers on Earth, simply walking past each other in opposite directions, nothing exotic, nothing close to the speed of light, just an ordinary walking pace. The difference in their respective nows, when you extend that disagreement out to something as far away as a galaxy on the other side of the observable universe, can amount to differences of entire days, which means that at this very moment, in someone else's perfectly valid present, events on the far side of the universe that have not yet happened in your present may have already happened in theirs. Not will happen, not are about to happen, have already happened for them right now, while for you, those same events are still sitting somewhere in the unwritten future. Two people, both correct, disagreeing about whether something is finished or hasn't started. Sit with that for a moment, because if that's true, and every experiment we have ever run on this says it is, then what does it actually mean to say an event is in the future? Future for whom? By what clock? Measured from where? This is the question that a mathematician named Hermann Minkowski picked up just 3 years after Einstein published his original work, and what he did with it changed physics permanently. Minkowski had been one of Einstein's professors, and when he looked closely at what special relativity actually implied, he realized that space and time were not two separate things that happened to interact. They were two aspects of a single, unified structure. He gave a lecture in 1908 that opened with a sentence that has been quoted in physics departments ever since: that space by itself and time by itself were doomed to fade away into mere shadows, and only a union of the two would preserve an independent reality. What he meant was this: there is no such thing as pure space and pure time separately. There is only space-time, a single four-dimensional structure, 3 dimensions of space and 1 of time, woven together into one geometric object. And once you accept that structure, the strange disagreement about simultaneity stops being a paradox and starts making a different kind of sense. Different observers aren't disagreeing about reality. They're just slicing the same four-dimensional structure at different angles, the way two people looking at the same loaf of bread might cut their slices at slightly different angles and end up with different shaped pieces, even though it's the exact same loaf. And this is where we arrive at the idea that gives this video its title, the idea that has quietly reshaped how a large number of working physicists think about existence itself. If space and time are genuinely unified into one single structure, and if there is no universal now slicing through that structure the way Newton imagined, then what happens to the past and the future? In Newton's universe, the past is gone, destroyed, no longer real in any sense, and the future is unwritten, not yet real, waiting to be created moment by moment. But space-time, as Minkowski described it, doesn't work that way. It doesn't have a privileged slice called now, moving through it like a torch sweeping across a room, illuminating what's real and leaving darkness behind. The whole structure, past, present, and future together, simply exists all at once, the way every point on a map exists at once, whether or not you happen to be looking at it right now. This idea is called the block universe, or Eternalism, and it is one of the most quietly radical conclusions in the history of physics, because it means that your 10th birthday and the moment of your death are not separated by some fundamental difference in reality. They are simply different coordinates in the same four-dimensional structure. The way Paris and Tokyo are different coordinates in the same three-dimensional structure. You don't say Tokyo stops existing the moment you leave it. In this picture, physicists argue there's no principled reason to say your childhood stops existing the moment you leave it either. It's not gone. You're simply no longer located there. Two physicists in the late 1960s, working independently, a Dutch physicist named Cornelis Reitdijk and an American philosopher named Hilary Putnam, pushed this logic to its natural conclusion and arrived at something almost impossible to argue against once you accept the starting premises. If simultaneity really is relative, the way experiments confirm it is, and if two different observers really can have two different, equally valid versions of now that disagree about what has already happened somewhere far away, then for that disagreement to be logically consistent, the events in question have to already exist in some sense for both of them. One observer's future has to already be sitting there, fixed and complete, in order for it to be simultaneously part of another observer's present. If it weren't already there, waiting, fixed, then the two observers wouldn't just have different opinions about time. The universe itself would be contradicting itself, being both determined and undetermined depending on who was looking. Physics doesn't tolerate that kind of contradiction. So, something has to give, and what gives is the intuitive idea that the future is open and unwritten. The argument suggests, with real mathematical force behind it, that it isn't. Now, if you've been listening carefully, a question has probably already started forming somewhere in the back of your mind, and it's worth pausing on deliberately because it's one of the genuinely difficult, unresolved questions this entire subject raises. If the future already exists in the same sense the past does, fixed, complete, sitting there in the structure of space-time waiting for you to arrive at it, rather than being created by you as you go, what does that mean for the feeling of choosing? Every decision you've ever made has felt, from the inside, like an open branching point, a moment where multiple futures were genuinely possible, and you picked one. If the block universe picture is correct, was that feeling ever accurate? Or is what we call a decision simply what it feels like, from the inside, to move along a path that was already fully determined the moment the universe began? That's not a question physics fully answers, and it's not one this video is going to pretend to answer either. It's one worth sitting with, honestly. What do you think is actually happening in the moment you make a choice? And does it change anything about how you choose to live if the choice was, in some deeper sense, already made? Let's go back to the physics, because there's a piece of this that is even more personal than the abstract geometry, and it comes from Einstein himself, near the very end of his life. In March of 1955, Einstein learned that his closest friend, a man named Michel Besso, had died. He wrote a letter of condolence to Besso's family, and within it, he included a sentence that has been quoted, argued over, and sat with by physicists for 70 years. He wrote that people like himself, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein himself would die less than a month later. This wasn't offered as poetry, and it wasn't offered as a comforting turn of phrase to soften a grieving family's loss, even though it has often been read that way since. It was, as far as anyone can tell, a literal statement from the man who built the theory, describing what he understood that theory to actually imply. In the four-dimensional structure his own equations described, Besso hadn't been erased. He simply existed at a location in space-time that Einstein, still moving forward along his own path through that structure, could no longer reach. The version of Besso sitting in his study, laughing at an old argument about physics, was, in this picture, no less real than the version of Besso who had just died. Just no longer accessible. That is either one of the strangest, most beautiful ideas a human being has ever offered as consolation, or it's one of the strangest, most difficult ideas to actually live with. And reasonable people land in very different places on which one it is. Some people find real comfort in the thought that nothing is ever truly lost, that every conversation you've ever had, every ordinary Tuesday afternoon, every person you've loved and lost still exists somewhere in the structure of space-time, fixed and unerasable, the way a photograph exists even after the moment it captured has passed. Other people find that idea cold, even unsettling. The thought that if everything is simply a fixed point on a map you can no longer travel to, then loss is permanent in a different, perhaps crueler way, because the thing you lost isn't gone, it's just forever out of reach. There isn't a correct answer to which of those reactions is the right one to have. It's worth asking yourself, honestly, which one is closer to how you'd actually feel, sitting with this idea at 3 in the morning. Let's take a breath here, because we're about to go somewhere even stranger, and it helps to have solid ground under you before we do. Everything we've covered so far comes from general and special relativity. The physics of very large, very fast, very massive things. Planets, light, gravity, galaxies. But there is another branch of physics that describes reality at the smallest possible scale, the scale of individual particles. And that branch is quantum mechanics. Quantum mechanics has been tested more precisely than almost any other theory in the history of science. And here is the deeply strange part of tonight's story. When physicists have tried to combine general relativity, the physics of the very large, with quantum mechanics, the physics of the very small, into a single unified description of the entire universe, the equation they arrive at does something nobody expected. It loses time entirely. This is called the Wheeler-DeWitt equation, developed in the late 1960s by physicists Bryce DeWitt and John Wheeler. And it was an attempt to write down a quantum description of the whole universe at once. Not just a small system inside the universe, but everything, including space-time itself. When you do the mathematics correctly, applying the rules of quantum mechanics to the entire cosmos as a single system, the variable that represents time simply drops out of the equation. Not because anyone chose to remove it, not because it was simplified away for convenience. It disappears as a direct mathematical consequence of treating the universe as a whole, self-contained quantum system. Physicists call this the problem of time, and it has remained one of the deepest unresolved puzzles in theoretical physics for more than 50 years. If you write down the equation that's supposed to describe literally everything, using the two most well-tested frameworks physics has ever produced, and time isn't in it, what does that tell you about how fundamental time actually is? There's a way to think about why this might happen that doesn't require you to believe reality is some kind of frozen, meaningless void, and it comes from a working theoretical physicist named Carlo Rovelli, one of the founders of an approach to quantum gravity called loop quantum gravity. Rovelli's argument, laid out across years of research and in his widely read book, The Order of Time, is that time isn't a fundamental ingredient of the universe at all. It's something that emerges, the way temperature emerges from the average motion of countless individual molecules, without any single molecule itself having a temperature. No single molecule is hot or cold. Temperature is a statistical property that only makes sense when you're looking at a huge collection of them together, and you don't have, or don't care about, the precise details of every individual particle. Rovelli's proposal is that time works the same way. At the deepest, most fundamental level of reality, there may be no ticking clock at all, only a vast web of relationships between physical variables, none of them flowing in any particular direction. What we experience as the forward march of time, he argues, only appears once you're looking at the universe from the limited, blurry vantage point of a system like a human brain that can't track every microscopic detail at once. Time, in this picture, isn't an illusion exactly. It's closer to what temperature is, something completely real and completely consistent, but only at a certain scale, only from a certain vantage point, and not a basic building block of reality itself. This connects directly to something you've probably felt your entire life without ever having a name for it. The fact that time seems to have a direction. You remember yesterday. You don't remember tomorrow. An egg breaks into pieces on the floor with ease. It never spontaneously reassembles itself back onto the counter. Coffee cools down in a room. It never spontaneously heats itself back up by pulling warmth out of the surrounding air. This one-way street is called the arrow of time, and the explanation physics offers for it comes from a 19th century physicist named Ludwig Boltzmann, and it comes down to probability, not to some built-in cosmic rule that time has to move forward. Think about a box containing 100 marbles, half of them red, half of them blue. If you very carefully arrange them so that all the red marbles sit on one side of the box and all the blue marbles sit on the other, you've created a highly ordered, highly specific arrangement. There's essentially only one way, give or take, for the marbles to look like that. Now shake the box. Within seconds, the marbles scramble into a mixed, disordered arrangement. And here's the key insight. There isn't just one way for the marbles to look scrambled. There are an almost incomprehensibly large number of different scrambled arrangements that all look, to your eye, equally mixed. Ordered arrangements are rare. Disordered arrangements are common, simply because there are so many more of them. So if you shake the box randomly, you will overwhelmingly tend to end up in one of the countless disordered states, not the one, single, perfectly ordered state. This tendency, systems drifting from rare ordered configurations toward common disordered ones, simply because there are vastly more ways to be disordered than ordered, is called entropy. And Boltzmann showed that it consistently increases in any closed system over time. Physicists now believe this steady increase in disorder is the actual source of the arrow of time you feel every single day. You remember the past and not the future because the past, relative to now, was a lower entropy, more ordered state. And your brain, itself a physical system obeying these same statistical rules, can only form records, memories, in the direction of increasing disorder. The universe isn't fundamentally built with a rule that says time has to move forward. It's simply, overwhelmingly, statistically more likely to be found drifting from order into disorder than the reverse, and that drift is what you experience from the inside as time passing. But here's where this gets stranger still. Because if the arrow of time really is just a statistical tendency rather than a fundamental law, it raises an uncomfortable question that Boltzmann himself struggled with for the rest of his life, and never fully resolved. If disordered states are simply more common, if there are more ways to be a mixed bag of marbles than a perfectly sorted one, then why did the universe ever start out in an unusually ordered, unusually low entropy state in the first place? The Big Bang, by every measurement we can make, appears to have begun in an extraordinarily ordered, extraordinarily low entropy condition. A condition so specific, so improbable if you imagine it as one random outcome among countless possible starting configurations, that physicists still don't have a fully settled explanation for why the universe started that way, instead of any of the vastly more probable, more disordered alternatives. This is sometimes called the past hypothesis, and it remains one of the genuinely open frontiers of cosmology. The arrow of time you feel every single moment of your life is running on rails that were laid down at the very beginning of the universe, for reasons nobody has yet fully explained. Let's step back from entropy for a moment and return to something more directly experiential, because there's one more piece of this puzzle that lives not in the equations of physics, but in the architecture of your own brain. And it might be the strangest piece of all, because it means the now you're experiencing. This very second isn't quite what it feels like either. Your brain does not receive information about the world instantly. Light from your eyes, sound from your ears, pressure from your skin. Each of these signals travels through different neural pathways at different speeds. And each one takes a measurable amount of time to reach the parts of your brain that process it. A sound reaching your ears is processed faster than an image reaching your eyes. A touch on your hand is processed faster than a touch on your foot, simply because of the distance the signal has to travel through your nervous system. If your conscious experience simply reported these signals the instant each one arrived, the world would feel fractured. Sound and sight and touch constantly out of sync with each other, arriving in a scattered, staggered mess. But that isn't what you experience. You experience a single, unified, seamless present moment. Sound and sight and touch all arriving together, perfectly synchronized. The way your brain achieves that seamlessness is by waiting. It holds the faster arriving signals back, just briefly, until the slower ones catch up, and then it assembles everything together and hands you the finished result, labeled as now. Neuroscientists estimate this assembly process takes somewhere in the range of tens to a few hundred milliseconds, depending on which sensors are involved. Which means the present moment you are experiencing right now, listening to this, is not actually the present. It's a carefully reconstructed, slightly delayed rendering of a moment that is technically already past, smoothed over and presented to you as if it were live. You have never once, in your entire life, experienced the true present. You have only ever experienced your brain's best split-second reconstruction of a moment that already, technically, belongs to the past. There's a related experiment that makes this even more concrete. In the early 1980s, a neuroscientist named Benjamin Libet designed a study where people were asked to flex their wrist whenever they felt like it, with no external cue, purely on their own spontaneous impulse, while watching a fast-moving dot on a clock face, so they could report the precise instant they felt they had decided to act. At the same time, Libet measured the electrical activity in the region of the brain responsible for initiating movement. What he found was that this readiness signal, the brain activity associated with preparing to move, began several hundred milliseconds before the person reported consciously deciding to move at all. The brain, in some meaningful sense, had already started the process of acting before the conscious mind reported having made the choice. This experiment has been debated, refined, and reinterpreted extensively in the decades since, and it doesn't settle the question of free will on its own. That's a much larger and more contested conversation than a single study can resolve. But it does suggest something worth sitting with. The tidy, linear story you tell yourself about how a decision happens. First I decide, then my brain acts, then my body moves, may not accurately reflect the actual order of events inside your own skull. What does it change for you? If the feeling of deciding sometimes arrives after the decision has already begun. So here is where all of this leaves us, gathered together in one place. Relativity tells us there is no single universal now shared by the whole universe. That simultaneity itself depends entirely on how you're moving, and that two equally valid observers can genuinely disagree about what has and hasn't happened yet. Minkowski's geometry tells us that space and time aren't separate stages for events to unfold on, but a single, unified, four-dimensional structure, and that within that structure there may be no principled reason to say the past has been destroyed or the future doesn't yet exist. Only that we, as observers moving through it, occupy one particular location within it at a time. The deepest attempts to unify quantum mechanics and general relativity produce equations where the time variable disappears entirely, suggesting that what we experience as time might not be a basic ingredient of reality at all, but something that emerges, the way temperature emerges from countless individual particles, only at certain scales, from certain vantage points. Entropy explains why the arrow of time points in the direction it does, but leaves open the deeper question of why the universe began in the astonishingly ordered state that set that arrow in motion in the first place. And your own brain, moment to moment, is quietly constructing the very feeling of now you're using to process all of this, assembling it from fragments that technically already belong to the past by the time you become aware of them. None of this is offered to you as a trick or a hidden truth someone tried to keep from you, or a reason to distrust the physicists and neuroscientists who spent their careers carefully working this out. It's offered to you exactly as it is, the honest, tested, still incomplete frontier of some of the hardest questions human beings have ever asked. Nobody currently working in physics claims to have the final answer to what time actually is at the deepest level of reality. Rovelli thinks it's emergent, a kind of blur that appears once you stop tracking every detail. Others think there's more fundamentally there than that time carries real physical weight of its own. The honest answer tonight is that this remains open, genuinely, actively open, argued about in journals and conferences by people who have devoted their entire working lives to it, and still haven't landed on a shared conclusion. Maybe that's the part worth carrying with you as you drift off tonight. Not a tidy answer, but a wider frame. Somewhere, right now, in a present moment that is genuinely physically different from yours, someone else's now is unfolding at a very slightly different rate, shaped by how fast they're moving and how deep they sit in a gravitational field. And neither of you is more correct than the other. Somewhere in the four-dimensional structure that you are, at this very moment, moving through, every ordinary afternoon you've ever lived may still, in some sense, physicists are still arguing about, exist, fixed, complete, unerasable, simply no longer within reach. And the version of now you're experiencing as you listen to this final sentence was never quite lived to begin with. It was built quietly, in the dark, by a few hundred milliseconds of your own brain doing exactly what it has done every second of your entire life, without you ever once noticing the seams. Whatever time actually turns out to be, it has carried you here, to this exact configuration of thoughts, on this exact night, listening to these exact words. That much, at least, is not an illusion. Rest well.